Okay, welcome to part 3, where we're going to look at how do enzymes act as catalysts. So first we're going to compare and contrast the old lock and key model with the new induced fit model. We're going to explain in general how enzymes are able to enhance the rate of reactions and explain the roles of coenzymes and cofactors in enzyme catalysis. So you may have heard of the lock and key model, and the idea of that was that an enzyme and a substrate will fit together like a lock and a key. So the enzyme is very rigid and it has some hole in it that the substrate can just magically fit into. And other substrates in the solution cannot fit in because this is special for just the substrate of the enzyme. And that is why enzymes catalyze typically only one reaction, because they can only fit one substrate. Okay, the purple ones. Okay, so that's the lock and key model. Enzymes are rigid, substrates are rigid, it fits in like a lock and a key. You turn the key and then the product happens. Okay. In the induced fit model, again, we have the enzyme plus substrate, and this is based off of the lock and key model. But after we were able to get more pictures of enzymes in different forms using X-ray crystallography, so I'm going to just make a note of this, X-ray crystallography. So X-ray crystallography is like a photograph of an enzyme or a protein. So we're able to get those. So you purify the enzyme and basically snap a picture of it. You can look at its 3D shape. You can get these pictures with the substrate and without. But recently we've also had work with NMR, solid state NMR and other types, and this is like a movie of an enzyme. So when we add in the substrate to these enzymes, what we see is that the enzyme is really dynamic and it's constantly moving. And we weren't able to get that with still photographs, but we could understand that using nuclear magnetic resonance NMR, which you learned about in organic chemistry. And this is really like a movie. So this is really dynamic. Okay, so this is where this information is coming from. So this is more like photograph, right? We see the start and the end. Something happens in the middle, we're not sure what, but we think that the enzyme is static. Now we know that the enzyme is dynamic. So what happens in the induced fit is that the enzyme is really flexible. It's taking on a variety of conformations. So sometimes it's in the appropriate form, sometimes it's in a closed form, sometimes it's like partially there. It has a variety of different forms. And the substrate in solution is kind of floating around in different forms as well, and eventually it works out such that it will bind at the right enzyme at the right moment. This enzyme will continue to move until it makes the product. So the induced fit is sort of, as the substrate binds, it sort of induces its fit in the enzyme. The enzyme is flexible, it is not rigid, like in the lock and key model. And this is based on evidence from X-ray crystallography and nuclear magnetic resonance NMR. Okay. So in terms of energy, the enzyme is going to bind the substrate. And so it has to sort of destabilize the substrate in order to mimic the transition state. So then we're going to get an enzyme substrate complex that mimics the transition state. It kind of distorts the substrate, and then the enzyme must be able to release the product. So this is the general path of an enzyme that we're talking about. So how does this really occur? And this happens in a few key ways that you can remember. Generally, hold on. Number 1, something called electrostatic catalysis. So what this is, the enzyme has to have some pocket in it that stabilizes the transition state. And this likely, you don't want to form a covalent bond with the transition state because it has to make the product to release it. So this means that the enzyme uses non-covalent bonding to create a distortion in the transition state. It distorts the substrate. Non-covalent bonding to stabilize the otherwise high energy transition state. So that's electrostatic catalysis. That's one strategy that enzymes use. The second strategy is what I sort of just alluded at. It's called the induced fit, right? So the substrate can bind an enzyme that's maybe not 100% ready to perform catalysis, but it can create its own pocket for the enzyme, right? So this is sort of like the distortion of the substrate. So the enzyme distorts the substrate. Distortions of substrate upon binding. And the enzyme plus substrate complex. And this is enzyme substrate complex. Okay. 3. There's one strategy. So we're destabilizing the substrate, we're stabilizing the transition state. So remembering back to that reaction coordinate diagram, we are making it more favorable to go to the transition state. So more molecules would be likely to make it to the transition state and then make it to product. Okay. The other way that enzymes work, if you consider it, in solution, molecules they're limited by diffusion. If two molecules need to react together, they must first be in proximity to each other. So enzymes can speed up chemical reactions by taking these molecules and putting them in one place together. So they optimize proximity. And so this makes a very favorable change in the entropy of the situation. So we want, in this particular instance, we want the two molecules to be close together, so it minimizes the delta S. Minimizes the change delta S of the transition state. So we want the transition state to more closely look like the product. And enzymes can do that by keeping everything together in its pocket. So decreasing the entropy in this situation actually speeds up the reaction. I know, right? We just learned that increasing entropy is favorable, but in this case, decreasing entropy is favorable. Speeds up the reaction. And then finally 4, something called covalent catalysis. And what this means is that when the substrate is bound, the enzyme is able to make different intermediates, make more favorable intermediates. Favorable intermediates in order to sort of push the substrate intermediate. And so this sort of pushes the substrate to the product. And so this is ES becoming product and enzyme. Okay. So these 4 strategies are, in general, how enzymes are able to enhance the rate of reactions. And so we can go in and talk about specifics and look at each enzyme and see some combination of these, even if it doesn't necessarily happen in all enzymes at all times. These 4 are the most general strategies on how enzymes are able to take a substrate and make a product very, very quickly. So many enzymes require the use of cofactors and coenzymes. And a lot of people use these two words interchangeably, cofactor and coenzyme. But in some books, cofactors are inorganic and coenzymes, such as vitamins, are organic. But some books use them interchangeably. So be aware that there is technical definitions, but using them interchangeably, lots and lots of people do that. It's not the biggest of deals. So as I mentioned before, some of the best examples of coenzymes are the vitamins, right? So this is why you actually take vitamins, because vitamins are used by enzymes in order to perform catalysis. And many, many organisms are actually not able to synthesize their own vitamins. So that is why it's important to eat a variety of different foods every day, because different foods have different vitamins in them, because different organisms can produce different ones. So as long as you're eating a variety, it is unlikely that you would actually need a vitamin. Cofactors are typically things like metals. So these two are big in enzymes. Also, coenzymes such as like NADH, these can be small molecules that are also organic. Sometimes these are also called cofactors. So small molecules, vitamins, and metals. What these all have in common is, like the enzymes, these are not consumed. And actually, many times, especially in like NADH, which then becomes NAD+, this is actually regenerated in the enzyme. Generated in the enzyme mechanism, because they are so important. Okay. So there's a huge list of coenzymes, a huge list of vitamins, and a huge list of metals, all of which are important for different enzymes. I also want to mention that metals. There are some enzymes that have covalently bound metals, and those are called metalloenzymes or metalloproteins. So a great example of this would be the heme group. So hemes are porphyrin rings found in your blood, right? So these metals can be used to coordinate oxygen for transport, and so if you are low in iron, you don't feel very well, and that's because these enzymes aren't able to do their jobs. If they don't have the metal, they cannot function. However, metals are important to many other enzymes that are not covalently bound, and so like metal ions, they can form covalent bonds, or they can also be used to coordinate other molecules. And this makes a lot of sense, right? Because metals have really, really strong charges. So metals can be used to coordinate water, and because water itself doesn't really fall apart very easily to form activated hydroxide, right? Some small portion of this happens, but a metal can add this pressure to the water in order to make this bond more easily breakable. So this is called activating water, right? So it's removing this H+ and making an OH- that can then attack a carbon, for example. Metal ions can also be used to coordinate ATP, because ATP has lots of negative charges, so we can add in some positively charged metals to coordinate the negative charges on the phosphates and keep ATP nearby for the reaction. And this can also be used to stabilize transition states substrates, products, that sort of thing. Anything that needs stabilization in the active site, we can stabilize by using metal ions. So we can use it for chemistry, like activating water, or coordination of molecules.